recording now.
Let me know when you're going to start. I'll let you know. Here.
It's running.
You're on the air. Hi. So it started. Welcome, fans from across the universe, to the first televised geometric representation series seminar meeting. So Jim and I have been wanting to talk about this stuff that we've been developing over the last few years, mainly him. And it seems interesting enough that I thought I'd switch over to a videotape format, and we're going to be full of problems and difficulties, and we may even want to move the classes, but it should be fun. So let me try to this hour sketch what I think some of the class is about. And then next week I'm going to be gone, and Jim will tell you a completely different idea of what the class is actually about. Then I'll come back, and then we'll fight it out. So the problem is there's just so many different tentacles to this project. It's a little bit hard to know how to chop enough of them off to get something manageable. But I think one thing that Jim and I agree on, probably not, is that one of the goals of this is to understand the relationship of quantum mechanics to classical mechanics, or maybe classical logic. So in math and physics, we think about symmetries acting on things, and we solve problems with the help of symmetries, where for starters I might use groups acting on things, but later we'll get into things like Lie algebras, or quantum groups, or fancier things. Let's say groups for now. So groups acting on things, a useful technique for simplifying problems, but the question is, what kind of things should they be acting on? And so there's sort of a dichotomy between whether you want to be a traditionalist of a certain sort, or whether you want to try to acknowledge that the world is quantum mechanical in nature. And in either case, you can have groups acting on these things. What are these things in each case? Well, in the classical case, I'm going to just say that they're sets. So you have the concept of a group acting as invertible transformations on a set. And then, of course, sets form a category where the things going between sets are functions. So the idea of a group acting on a set, a fancy way to think about it, is that you've got this category of sets, which has all the sets and all the functions in the world in it, and then you've got your group, say G. Well, a group is also a category. A group is the same thing as a category with just one object and all the morphisms invertible. So we can think of them both as categories, and then an action is just a functor from one category to the other. So the idea is, group has this one object, which we call dot, because it doesn't really matter what we call it, and then our functor sends that over to a particular set, R of dot. And then our group has a lot of morphisms, which we normally call the elements of the group, things like G, some element of the group, big G, and they get sent by our functor over to functions, R of G, from this set to itself, in a way that preserves composition and identity. And so this abstract group, this group that's just symmetries, but not of anything in particular, the symmetries, is getting incarnated as symmetries of some actual set by means of this action. Okay, so that's a very general pattern, and in fact, there was really nothing necessary about sets. We could be using other categories. And in the world of quantum mechanics, one of the things we learn, at some point I'm going to want to move to the right, and then, okay, yeah, I'm just going to hop up instantly. Okay. So in the quantum realm, we learned that systems are described not by sets, but by vector spaces, or you might want to say Hilbert spaces, but I'm trying to keep everything sort of pared down and simple as possible. Of course, there's a lot more to classical mechanics than sets, too, and there's a lot more to quantum mechanics than vector spaces, but allow me this parity simplification. So we have this category of vector spaces and linear operators between vector spaces, which is the quantum world in a very simplified nutshell. And when you're studying symmetries in the quantum world, you're studying actions of groups on vector spaces, or what you normally call them, representations of groups on vector spaces. And that's the same kind of thing that we had before, but replacing the category of sets by the category of vector spaces. So now you have a vector space, and for each group element, a linear operator from it to itself, in a way that preserves the group operations, identity and composition. Now, representations of groups on vector spaces is a very fashionable, sexy subject. Actions of groups on sets is somehow a little less fashionable. Somehow a near set doesn't seem interesting enough for people who consider themselves algebraics. So there's been a kind of denigration of this realm as compared to this realm. But in fact, they're very related, and what geometric representation theory is about, one way to say what it's about studying representations of groups starting from actions of groups, using actions as a springboard to understand representations. And you see what's so important about this from the point of view of physics is that it's also using classical ideas to understand quantum ideas. So, right, the key thing about a vector space is that you have the superposition principle. You can add vectors and multiply them by scalars. So we can get funny situations in quantum mechanics where you may want to take a cat, multiply it by I, and add it to another cat. You get a superposed cat, and that's very mysterious. Mysterious what that means. Over here in the realm of sets, you don't have those mysterious operations. Everything makes more sense. But in geometric representation theory, we'll see that a whole lot of what's going on here in the quantum realm is actually secretly visible already in the classical realm, but by means of some sneaky tricks that we'll have to get into. Not completely obvious tricks. Okay, now I'm gone. Oh, I'm back. So, segmentation is not how I eventually get to it. So what's the basic idea of geometric representation theory? Well, if you're a category theorist, you should instantly guess from what I've drawn that we're thinking about actions of groups on sets, and we're wishing we could use them to understand representations of groups on vector spaces, right? So what do we wish we had? A vertical arrow going down. Hey, you guys can talk too. The mic can pick up everything. And we're supposed to have a lot of talking going on. Yeah, so you wish that you had an arrow going down here, and in fact you do have an arrow going down there. What's the most famous arrow down there? From sets to, what's the most famous functor from sets to vector spaces? Sorry? Free construction. The free construction. So you give me a set, and I cook up a vector space whose basis is that set. And so you give me some set X, and I form a vector space whose basis is that set. I don't even know what notation is best for that. I'm going to call it, and this may be evil in certain senses, I'm going to call it C to the X. So it's the X-dimensional vector space, if X was the cardinality of the set. So it's important to note that I do not mean all the functions from X to C. I do mean all the functions if X is finite, but if X is infinite, I just mean the functions that are vanished except on finite points. But anyway, well, in fact, mainly we studied really simple things at first. When we studied finite sets and finite dimensional vector spaces. And then you don't have to worry about this so much, or maybe in some sense you have to worry about it more, because you can get more confused about the difference between functions on a set and the vector space and space that is set. They will be isomorphic in the finite case. But anyway, I'll just use that notation. Partially because I will often denote an n-element set, my own favorite n-element set, I will often denote it just by n. That's one of the things that Jim taught me. And so then this is called d to the n. So n just means the d n-element set. D to the n means d n-dimensional vector space. And if you ask me which one, I'll just tell you, don't ask me that question. This is my favorite one. So what this means, you see, is that as soon as I get an action of a group on some n-element set, I get an n-dimensional representation of the group, where it's a sort of boring kind of representation where the group elements just permute the basis elements. But the idea of geometric representation theory is that you can go a shockingly long way towards understanding arbitrary representations by understanding those ones. And in some particular cases, you can sort of go all the way. So now, so one of the kinds of things we need to do is talk about lots of actions of groups on sets and what kind of representations we get out of them. And I want to talk about some examples. So I guess there's sort of two kinds of examples that I will start out with. Because a lot of the interest in the subject is not general abstract nonsense, it's specific abstract nonsense. So if we are studying groups acting on sets, particularly finite sets, we would like to find some particular good examples of groups that do that, and what are the sort of best examples. Symmetric groups. Yeah, you'll notice the whole name symmetric group is pretty bizarre, right? Because group is something that describes symmetry. So a symmetric group is sort of like saying a really groupy kind of group. But that's in fact what symmetric groups are. They're groups whose sole job in life is to act on n-element sets, because they're the group of all the automorphisms of an n-element set. So the symmetric group of all permutations of an n-element set is one of our main examples to get going with. Now, Jim always uses a different terminology for the symmetric group Sn, and I think I want to go along with him here. And maybe someone else can guess what the notation is. So let me try to give you all an even footing on guessing this. So you see, what we're systematically doing here is something called categorifying. You may think of n as a number, an element of the set of natural numbers. But here I'm using it in a different way to mean an object of the category of finite sets, some particular n-element set. So numbers are going to sort of systematically get promoted to objects. And things that normal people do with numbers are going to get systematically promoted to objects or things like that. So what should we call Sn? So there's a certain number, n factorial, or n bang. Yeah, that's right. So you learn about this number, n factorial, or n bang for short. But we're actually going to think of it as the name for the group. So that'll just be our terminology there. And we'll later see that this is very nice, because all sorts of fancy combinatorial formulas involving binomial coefficients and factorials and things, you can systematically categorize the whole formula. So everything in the formula, the summation symbol, the division symbol, the factorials, they all now mean various operations on sets. So this is just the tip of the big iceberg. Okay, Prasad, this is going to really, challenging today. We need someone who like hates mathematics, just doing that job, but loves videotaping mathematics. Right. So, okay. So this thing, okay, this acts on N. So there, we already get a representation of it on C to the N. Let's just look at that for a second. So, in a simple example, say 3 bang acts on C to the 3. Okay, so it does it in the obvious way, just by permuting the 3 coordinate axes. So, one of the things that people in group representation theory like to do is see if group representations are irreducible. So this is an operation of direct sum of group representations. And in the case of finite groups, a representation is irreducible precisely when you can't chop it apart by direct sum into smaller representations. Technically, that's called indecomposable, but it's the same as irreducible in the finite group case. So, is this representation irreducible? Why not?
You can exhibit a one-dimensional representation inside it.
So it has a one-dimensional sub-representation sitting inside this three-dimensional representation. How do you get that one-dimensional rep sitting inside there? Sorry? The diagonal, yeah, or, so if you think of C3 as functions on the three-element set, then they'd be the constant functions. If you permute the elements in the set, the constant functions are invariant under that. Or diagonal, I'm not sure in what sense it's diagonal. Main diagonal, yeah, I'm not quite sure. So
or a triple world with numbers of.
Yeah, so diagonal is cube. So, okay, a triagonal. So, right. So those guys, and then some other two-dimensional subspace. You can always pick a complementary, invariant complement in the case of finite group representation. So this three-dimensional representation will split as this thing, one-dimensional subrep, and then this two-dimensional rep. This one turns out to be irreducible to this two-dimensional one. But we don't need to worry about that too much. That two-dimensional representation is the thing you get where you draw an equilateral triangle centered at the origin. Permutations of the three-element set act as symmetries of that triangle, and then they move the plane around. And that gives you a two-dimensional representation. This looks like a real plane, but it's complex two-dimensional. You're right. That doesn't matter so much. What mainly matters is that you shouldn't expect to get very many irreducible representations of groups out of this trick of turning group actions into group representations. In fact, what can you say about your chances of getting an irreducible representation by means of this method here? It's always going to be susceptible to this trick, so you're never going to get an irreducible representation unless two is a very large number. No, unless you're talking about one. Unless you're talking about if you're acting on a one-element set where the constant functions on it are all the functions, then you get an irreducible trivial representation. But yeah, apart from that stupid case, you'll never get an irreducible representation this way. So you'll always have this challenge of taking these nice representations we get from actions and then chopping them apart into these little irreducible pieces. And the idea of Hecke operators, which will be one of the main themes of this class, seminar, is cooking up operators that will take these representations and allow us to project out these various irreducible pieces, but getting those operators in a nice way based on set theory, based on thinking about groups acting on sets. So that's one thing to say. Okay, now I'm going to slide over a bit more. So n bang acts on n, but that's not enough to really get us all the representations of of n bang. We need other tricks. And so we use this basic trick here, which is that whenever you have a group acting on an n-element set, and you have some kind of structure that you can put on that n-element set, then your group will act on the collection of those structures. So someday I'll tell you exactly what a structure is. You can define it in a pretty precise way. But for now, you should just think of it maybe by means of example. So one kind of structure you can put on an n-element set is a two-coloring, a way of labeling all its elements by red and blue. So a structure you can put on an n-element set. So if I have an n-element set, permutations act on that, and therefore they act on the set of two colorings. So that's a way to get a new group action from an old one by means of a structure. And that's the main way that we get lots of other representations. So in particular, so if G acts on X and S of X is some set of structures we can put on X then G acts on S of X. And if you wish that that was a real theorem, you need just to make precise the definition of structure. One way to make precise the definition of structure is to make this be the definition of structure, which may seem a little bit unfair and deprive the theorem of any theoremhood, but anyway, that's one way you can do it. There are others. So in particular, we'll get lots of representations of n bang. Well, we'll get lots of actions of n bang, and thus representations, from structures that we can put on an n-element set. So one thing we're going to do is describe a sufficient collection of structures that you can put on an n-element set to get all the irreducible representations of n bang. You don't get the irreducible representations directly. As I said, you hardly ever get irreducible representations from this trick. But you get a bunch of representations, and then if you chop them apart into their irreps, you get all the irreps. From what kind of structures do we need? So here's the kind of structure that we'll be talking about a lot. So we'll get them from these structures called Young diagrams. So I'll define an uncombed n-box Young diagram. And then later I'll tell you about what the combed ones are, and those are the more familiar n-box Young diagrams. So what it is, well, it's just an incredibly obfuscatory term for a collection of numbers that add up to n. So a collection of
Like a list.
a list, n1 through nk, of positive integers that add up to n. So n1 through nk add up to give n. And why in the world do we call this a Young diagram? Well, it's because we will draw a bunch of boxes, a row of boxes for each number n1 through nk. So n1 here is 3, n2 is 2, n3 is 1, and n4 is 5. And we're just drawing that as a bunch of boxes, by means of a bunch of boxes. sounds sort of childish. Maybe it is, but tradition. And it's probably really helpful. And so this would be an uncombed something or other box. 3 plus 2 plus 1 plus 5 is 11 box Young diagram. And we'd say it's combed, or we'd say it's just a plain old-fashioned Young diagram if these numbers are in decreasing order. So if n1 is greater than or equal to n2, is greater than or equal to n3, and so on, we just say it's a Young diagram. I was thinking of calling these uncombed Young diagrams old diagrams, so that I could refer to any old diagram and have it be something technically specific, but Jim didn't like that idea, so I won't use that. So I don't like negative attributes in general. Attributes that mean properties from something. They're a little tricky to work with logically, but we'll call it an uncombed diagram. So just somehow combing the diagram means putting the rows in decreasing order. That's the length. So this is a 4-row Young diagram we have here. Okay, now any such thing will give us a structure on an n-element set. And here's how. So given an uncombed n-box Young diagram, you see why I wanted to call it an old diagram. D, we define a D flag on an n-element set. Say an n-element set X. So it will be some kind of structure that we can put on this n-element set. And it's an incredibly simple sort of structure, but it is. There are different ways to think about it, but here's one I like. It's a collection of subsets, x1 contained in x2, contained in x3, and so on, up to xk, where xk is the whole set. So we're having a sort of increasing sequence of subsets of x, where, oh, and I guess just for cuteness purposes, we'll define x0 to be the empty subset. That will be empty. And just to bottom it out like that. Where the number of elements in xi minus xi minus 1, so the number of new elements that you're throwing in to get up to the set xi is the number of boxes in the ith row of your Young diagram. So what we're doing here is we're just taking our set and we're saying, well, I'll use the example we had where our first Young diagram had, the first row of our Young diagram had 3 elements, so we put in 3 into our smallest subset, and then the next row had 2, so we put in 2 more, and then the next row has 1, so we put in 1 more, and then the final row had 5, so we put in 5 more points. So this is some kind of partition. I mean, another way to think about it, equivalently, is it's a partition of our set X. But instead of thinking of it as a partition, I'm thinking of it as an increasing sequence of subsets. And that's because that other way to think about it will be really handy when we think about D flags not on sets, but on vector spaces. So this is, anyway, some kind of structure that you can put on an m-element set. And so therefore, because n-bang acts on your n-element set, then it will act on the set of these structures, and so you'll get a representation of n-bang from any uncombed Young diagram. So let's just think about that, a tiny amount. So suppose our Young diagram looks like this. So how many D flags are there on an n-element set? First of all, maybe it would help to know what n is.
Are there n bands?
Well, yeah, you're generalizing from my example. Where n is equal to 3. Right, yeah, that's right. So there are 3 of these structures on the 3-element set. And of course, it generalizes to other Young diagrams that are this long and skinny form. So then there are, but anyway, in this case, there are 3 factorial D flags on your favorite 3-element set, which is called 3. So a typical one of them would be a little bit like this. One, more typical. 3, 2, 1. No, that's not typical one up here. 3, 1, 2. So what that means, of course, is that we have this nested sequence of sets. First one of which is just 3, the next one is 3, 1. So we'll get a 6-dimensional representation of 3 bands by letting 3 bands act on this set of D flags, and then letting it act on the vector space scanned by that. So we'll get some 6-dimensional representation of 3 bands, right? It won't be irreducible, but the good news is that you can get all the irreducible representations of symmetric groups this way. So there's this theorem that will eventually prove, although I'll warn you that I guess Jim's favorite method of proving theorems, which I'm beginning to like too, is you don't prove them. What you do instead is you talk about them for so long that it just becomes completely obvious that they're true, and that you don't even want to prove them because it's too obvious. So I may never prove this theorem, but hopefully at some point it'll become painfully obvious. We'll see. I'm not sure. We really don't know where this path is going. But here's the theorem. So every irreducible representation of n bands, this is a weak form of this theorem, is a sub-representation of some representation of the representation of n band on C to the D of n. So remember, I use this notation, D of n being the set of structures of some sort on the n-element set. Here it's the set of these D flags on the n-element set. So for some uncombed, some uncombed Young diagram, D is the set of D structures. Now, in fact, you can do a lot better in stating this theorem. For starters, in this particular case, you can get away with just using Uncombed Young diagrams. In fact, the note is combed ones. And that's pretty easy to see. That part is very easy to see. So a combed one, remember, means that the length of the rows in the diagram is getting shorter, so it never gets longer.
John, backpack.
Sorry?
Backpack, right here.
So why is it enough? If you know the first theorem, why is the second little clause obvious? Why is this, in fact, this is Yeah, so if I have an uncombed diagram, I can always comb it. So if I have this kind of if I have this D here, and I have a D flag on an element set, it's the same as having a partition of the n element set into labeled parts, where the 2-element part, 4-element part, and 1-element part, and a 2-element part. That's just another way of thinking about it. But then I can take any such structure like that and turn it into a structure like this by relabeling the part. So the order really doesn't matter much here. So you may wonder, why are we even worrying about the uncombed ones? Well, we're going to worry about them for some slightly other reasons than this. But for this purpose, the combed ones are all equal. And in fact, this theorem works out much better than this. In fact, there's a one-to-one correspondence between the irreducible representations of n bang and the set of the combed n-box Young diagrams. So in fact, it's not just true that every theorem shows up inside one of these representations. Every one of these representations has its favorite irreducible representation trapped inside it, trying to get out. You know, they say every fat person has an in person inside them, trying to get out, but unfortunately release that elimination to get out. So that's the exact same thing with these kind of situations here. We've got these big fat highly reducible representations, but everyone has a particular irreducible representation sitting inside it in a very nice way. And so we'll get a one-to-one correspondence between the theorems and the Young diagram. Yeah?
What is D of n in the exponent of C?
Yeah, I said it in words but not in writing. The D of n is a set of D flags on n. So I'm in general going to make up all sorts of names for structures that I can put on an n-element set. And then if I have a structure called S, then S of n will be the set of those structures on the n-element set. Yeah. So this is one thing we want to get to. And so the trick is to see, first of all, how we find these irreducible representations inside the big ones. And then second of all, why we get all the irreducible representations in this way. But now I want to shift over to a slightly different flavor of example. I guess I did example 1 of a group, n bang. Right, so n bang was the group that more than any other group deserves to act on an element set. But I said, besides sets, one of the other things we're thinking about in this subject is vector spaces. And then this is a sort of weird twist here that I'm throwing in, but it won't seem weird once you really know where we're going, but ultimately it's rather weird. But anyway, what group likes more than any other group to act on an n-dimensional vector space? GLN, the group of all invertible linear transformations of an n-dimensional vector space. Yeah, so for any field F, we can look at all the invertible n by n matrices of F, we get GLN F, and this acts as linear transformation, so it has a representation on the vector space F to the n. Now, you could say, oh, now we switched over to thinking about groups acting on vector space. But if you want, you can still think of this as a group acting on a set. So think of this as a set. And especially true if F is some weird field, like the field with 19 elements. You're not studying complex representation vector spaces anymore. Right? You're studying complex representation groups anymore. You're studying groups acting on some finite set. So this is another source of lots of group actions on finite sets. Namely, this thing here, when F is a finite field. Luckily, you don't need to know much about finite fields to survive this class. Or at least I've managed to survive my studies of subject without learning much about finite fields. So you may be sort of terrified of these finite fields, but you don't need to know much you really just need to know sort of about how many there are, or how they're parameterized. So there's a finite field. There's a field with Q elements. Called FQ. Whenever what? So what Q's can you use? Yeah, Q the prime power. I think that's all you need to know about finite fields. So there's just one of them for every prime power. Upside isomorphism. It's a unique upside isomorphism field for each prime power. So, Q is not equal to 1? Yeah. Oh, well, yes, well, we'll see about that. But anyway, here, I'm certainly doing a demonstrated. So, I guess there's one thing else that's often good to know, which is that you definitely know what these fields look like when they just have a prime number of elements. Then it's just the integers mod p. For those fields, prime numbers of elements, they're like easy to calculate. But if you have to like start calculating with a field with 3 to the 47 elements, you'd actually have to find some polynomial of 347 that wanted to have 47 distinct roots, didn't have them yet in your 3-element field, throw in all those roots. And it's sort of hard to describe that in a very concrete way. So they tell me. Doing arithmetic in finite fields can be surprising. Luckily, we don't need to do much of it yet. I'm sure we would if we got far enough. Now what I'm going to do is I'm going to tell you what the concept of a D flag is in this context. So let D is the same kind of thing. Be an uncombed n-box Young diagram. And I'm going to tell you what a D flag on F to the n is. This is a different concept than before. For some strange reason, I'm using the same name, but we'll see why. So you see, we have this concept of the D flag in the world of sets, and now we're switching over to the world of these vector spaces. But you can just somehow hope that there's some analogy. So maybe someone can guess. So what would the D flag be in this case? It's nested subspaces. Modules? Well, what we're doing is vector spaces here. Modules over a field are just vector spaces. So you don't need to say modules. That makes it sound more terrifying when it even is, right? So they're just vector subspaces of this. F could be any field here. So we'll have nested subspaces. I guess I again want x0 to be 0, but now I need something else, zero-dimensional subspace. I want x to the n to be the big fat thing. Which big fat thing? Well, x, I guess I would call it the f to the n. xk, so there's k rows. And I should have been defining this for any n-dimensional vector space, not just Fn. So call this x and let it be any n-dimensional vector space. And we get slightly more generality that not every vector space is equal to Fn, but it's no big deal. So it's some nested subspaces such that what? The dimensions go up by the numbers of boxes in each row. So right, so now it's the dimension of xi mod xi minus 1 is supposed to be n sub I. Yeah, that's right. So subtraction turned into modding out and instead of cardinality, it's dimension. So, I'll have a lot more to say about this concept of flag. This concept turns out to be very geometrical in flavor when you think about it. But let's just do a little example to give you a feeling for some of the weird stuff that starts happening here. So I'll just ask you, so take D to be the same Young diagram that we looked at a little while ago. And I'll ask, how many D flags are there on F to the 3? Well, there'll be infinitely many unless our field is a finite field. So we'll make it have to be a finite field and let it have some number Q out. So we'll do a finite field. So let's figure this out. Okay? So the idea is, right, you've got this three-dimensional vector space, and a D flag in this case would be picking out a one-dimensional subspace sitting inside a two-dimensional subspace sitting inside the three-dimensional subspace. So I'm drawing my field as if my vector space was R3 here. We have the origin, the line through the origin, and then a plane containing that, and then the whole three-dimensional space. So that's what a D flag on R3 would actually look like. It actually looks a little bit like a flag, if you have a really good imagination, right? So a flag sort of looks like this. So it contains the origin, and then it contains a line, and then it contains a plane, which is even bigger. That's why it's called a flag. Sounds really lame, but that's okay. So, let's get that. So, but let's, in any event, let's count the D flags here. So first let's count how many lines through the origin there are in this vector space. How do you count the lines through the origin? Okay, so you suddenly spit out the answer, Q cubed minus 1 over Q minus 1. But now, explain to me how you got this answer. It's sort of like a little story into itself. So what does Q cubed minus 1 come from?
Any point other than the other.
Any point in the vector space other than the origin. Right? So a line will be determined by any non-zero vector. There are Q cubed vectors in here. That's what it sort of says. But subtract the origin, so we're left with Q cubed minus 1. So that's how many non-zero points there are, but that's redundant because lots of points lie on the same line. Yeah, you can rescale by any non-zero number. So there are Q minus 1 non-zero numbers. So any of those non-zero multiples of your given vector will determine the same line. So we're over-counting by a factor of Q minus 1. So that's how many lines there are through the origin in this three-dimensional vector space. Okay, so now we take that. Now we want to pick a plane containing that line. Now, so that sounds more complicated and confusing, but it's actually less. Yeah?
No, that's fine. So, same idea. We have to pick 2 points, those points, 2 non-linear points, those points.
Well, we know that one of them has to already be on our line. Well, we don't know that, but we might as well have.
So we
already have to pick this line, and now we're trying to pick a plane.
So we pick a point with the point not on that line, with that line?
So this sort of, yeah. That's basically right. You pick a non-zero point off the line. But then, of course, lots of different points would give you the same plane. So there's actually sort of a more elegant way to deal with this, so that you don't have to start worrying how many points are there on a plane that aren't on a line.
Well, but that's easy. It's just Q to the n minus Q to the something else.
it's easy, right, but it's not easy enough for me.
Okay.
Okay, I'll just tell you how I do it. None of you can do it the easy way. I'll tell you the easy way. So, I'm trying to fit this two-dimensional subspace that contains my one-dimensional subspace. So what I'll do is I'll take this space here we had and we'll mod out by the one-dimensional subspace. So now I'm left with a two-dimensional space. And I just need to pick a non-zero element of that. Right, so to pick a plane that contains a line, the same thing as to pick a line in the quotient space of the free space minus mod the line.
Not a point, but a line.
We'll pick a line because, because many different points would determine the same line. So how many lines are there in FQQ?
So Q squared minus 1 over Q minus 1.
Yeah, well, see, it's easier than the case before. In the sense that it's, now what we're doing here is we're picking a line for two-dimensional space, which is just our free space mod the line we've already picked. Okay?
Technically, you want the free space to do it. But
Yeah, so then we keep on going, but at this point, you'll notice it's sort of
there's only one choice.
one choice. But it's nice to write that anyway, because it's a factorial, so you give it away.
Those are the quantum features.
These, oh, you're giving them away, man. Oh, I'm sorry, folks out there in DB land, so people just can't be quiet. So yeah, so what I was going to ask you was, what does this converge to when Q approaches 1? So what does this converge to when Q approaches 1? It converges to 3 by somebody or other's theorem, the guy who figured out how to differentiate Q cubed. Okay, like and this converges to 2 because it's just the derivative of squaring. This converges to 1. Well, it was 1 all along. So this thing here converges plain old-fashioned 3 times 2 times 1 in the limit where Q goes to 1. So this is like some modified version of 3 factorial. And in fact, this number here is called 3 sub Q, the Q version of the number 3. Q integer 3. And this is called 2Q. It's called 1Q. And then this whole thing is called 3Q factorial. So the way that you count these D flags is using Q factorials. But the mysterious thing is that as Q approaches 1, these Q factorials approach the ordinary factorials, and we get back down to the answer to our set theoretic problem that we had before when we were counting flags on a 3-element set. But I hope you see why this is weird, right? Because Q equals 1 is a value of Q that you're not allowed to use when you're talking about finite fields with Q elements. But we do, however, so there's no such thing, so they tell us, school, as a field with 1 element. But we now seemingly have a guess, a weird guess, for what a vector space over the field with 1 element is, which is what? A set. Yeah, so a finite dimensional set is, for some bizarro reason, analogous to a finite dimensional vector space over the field with 1 element. A finite. Of course, when we work for infinite sets and infinite dimensional vector spaces.
You just said finite dimensional set.
Oh, a finite set, yeah, it does the two-dimensional. Yeah, finite set, right. So in fact, I'll leave it as an exercise, a non-official assigned exercise, for those of you who really want to understand this. To check that this thing I checked for this particular Uncombed Young diagram is actually true for all Uncombed Young diagrams. In other words, take any Young diagram, count the D flags on your vector space over FQ. You'll get some formula that involves Q factorials in a more complicated way than this. Then take the limit where Q goes to 1, and you'll be counting the D flags on the finite set. So this is a sort of a tip of an iceberg. And even that's the tip of a bigger iceberg, which is that the representation theory of groups and bang, acting on the n on the set, is closely akin to the representation theory of GLN FQ. And in some sense, one of the q-deformation of the other. This process of sticking q's everywhere is called q-deformation. And so that's one of the main themes of this class. Trying to understand q-deformation. So q-deformation shows up in lots of contexts, one of which is the theory of quantum groups. And so one thing you can think of this class is thinking about is like trying to dig beneath the surface of quantum groups and figure out what's really going on. Yeah. But we've dug so far deep that we may never get around to talking about quantum groups and never get back up. But we should talk about quantum groups eventually. Okay, now I want to say a little bit more about why this whole subject is called geometric representation theory. So far, there's just been a teeny little bit of geometry visible, which is, I guess I drew a picture of a flag. So that was, in fact, the geometry there. But I want to make it seem a little bit more like geometry. And so I want to talk about a little bit about projective geometry, which is what another way of thinking about what we're discussing here. So projective geometry was invented in sort of an informal way by Renaissance painters who were learning how to do perspective. And the way they learned to do perspective was by cheating. So what they did is they would have a scene they were trying to draw, and they would get some kind of sheet of semi-transparent paper and hang it up in between the painter and the scene that they were looking at, and then they do something. I'm not quite sure how. They feel like I'm taking a really long paintbrush and picking out little dots on the sheet of paper that would lie right in front of the thing you were trying to draw. So you kind of draw a cup to sort of trace the cup. But the cup's over on the other side of the room, and you're tracing it with a long brush. So you're basically looking at all the lines between your eye and various points on the cup, and then intersecting them with this plane, which is this piece of translucent paper, and again, getting a really accurate perspective picture of a cup. Yeah?
Some of those famous woodcuts actually showing this process.
Yeah, there's some really cool old woodcuts showing painters.
But the screen has some sort of grid on it.
Oh, that's true. At least that's the paint. Yeah, so I may be lying slightly. I've seen.
Well, no, I think that's
have a kind of grid.
I think the grid is what they use to help carry this process out.
Yeah.
Instead of a long paintbrush.
Yeah. Okay. So instead of like painting lovely, so
There's
that's
another
funny for
story
paintbrush.
about setting the lenses up in the window that actually projected onto their canvas to really make it do something.
Yeah. So there's different kind of things. So there's something called a camera obscura, which I don't quite know what it is.
Well, that's beginning to really be cheating. I mean, yeah.
Well, eventually you use a camera, right?
Yeah.
Then you're right. But this is like, but in fact, recently people have discovered that who's the one who painted the girl with a pearl earring? Vermeer? Yeah. So Vermeer was like recently discovered. I don't know how. So late, got caught using one of these devices to help draw the perspective in his painting. And then there was a big argument erupting, like, was he cheating? We thought he was a good painter, but he was cheating. These tools to help him. So I think, in fact, though, part of why it took so long to catch it, quote unquote, is that some of the painters did want to keep it secret how they did this, to make it seem more impressive. So one of the things about projective geometry that's very interesting is that this idea of the horizon. So like if you're drawing a painting of a big flat desert, it goes off to the horizon. It might look a bit like this, or at least part of it looks like this. And then if you had some train tracks in the desert, it would look like this. Well, I should be punching out much more. And so the parallel train tracks are meeting on the horizon when seen in perspective. And so one of the things that's interesting about projective geometry, when you do it really beautifully, is that every pair of points, every pair of lines intersects in some point, which could be at the horizon, it could be infinitely far away. And people of a more mathematical ilk like that a whole lot because there's this sort of annoying exception, right? Parallel lines don't meet at a point. So you have this stupid axiom that says lines meet at a unique point unless they don't meet at any point at all. Whereas the logical form of projective geometry is more beautiful. Any two distinct lines meet in a unique point. And one reason why that's so beautiful is that if you switch the words point and line, it's still true. Any two, well, we may want to switch some other word for decorative purposes, any two points determine a unique line. And so there's a symmetry between lines and points in projective geometry. It's obscured in Euclidean geometry. And the idea of how it works is this, when it got developed further, is you invent this concept of the projective plane, and the projective plane, I'll do the real projective plane, RP2. What it is it's the set of lines through the origin, or let's say 1D subspaces, of R3. And the way it works is, well, I just sort of erased the picture of how it works, but what you do is you take your origin here, you look at all these lines through the origin, and then what you do, you say, what in the world does that have to do with a plane? Why should we call the set of the lines of the 1D subspaces, what should we call a plane? Well, to see why, you just pick a plane in 3 space that doesn't contain the origin. So like this desert scene that I just erased, and most lines through the origin will intersect that plane at a unique point. Some may not intersect it at all. So most of the lines through the origin, all except the set of measure 0, will be identifiable with points on an ordinary plane. So here's our ordinary plane, R2, and points in R2. Most of them are corresponding to points in R2. There are just a few that don't. There are a few lines that don't intersect R2. And what are they giving us?
The circle.
They're giving us the horizon, or the circle at infinity. Yeah, so as you let this little cowboy here run off to the horizon, right, the line is moving until it becomes finally parallel to this plane. So the points on the horizon of your scene correspond, which aren't really in R2, but in sort of limiting points at the edge of R2, so to speak. They're corresponding to the lines, the 1D subspaces that don't intersect R2. And there's a circle of them, but it's a slightly funny circle because, why is it a slightly funny circle? You're right, that what we're saying here is that there's a way to think of R2 as R2 together with a circle.
That is the one.
Yeah, right, because when you have this line that doesn't intersect the plane, you can't really tell whether it's supposed to correspond to that point or that point. So in terms of this cowboy desert metaphor, you have to imagine like people say, hey, where did that guy go? He says, oh, that way. So it's like, I knew he took a train on this, went on this track here, but I just forgot which way the train went. So all I know is he's like off on the horizon, either that way or that way. I can't tell you which. So you get not the obvious looking circle of points on the horizon, but with typical points identified. And that's actually, that's the thing that's actually RP1. With that circle there. So what we're getting here is a kind of way of describing projective two-dimensional geometry in terms of one-dimensional subspaces of three-dimensional vector spaces. And that's how projective geometry works in general. Okay, I'll move over here. So the idea is that we define, for any field, we define Ft n minus 1 to be the set of 1D subspaces of the vector space F to the n. So a point in this projective space, Fpn minus 1, which is really a line through the origin in Fn. A line in Fn minus 1, we define that to be basically a two-dimensional subspace of Fn. A two-dimensional subspace contains a bunch of one-dimensional subspaces, so a line would contain a bunch of points. So there's just a dimension shift by one going on here when we go from n-dimensional vector space geometry to n-1 dimensional projective geometry. So for example, like if we're doing our same example here, here's my picture of most of RP2, just the RP part. So it has lots of points. It has lots of points which are really lines through the origin in R3. But it also has a bunch of lines which are really planes through the origin in R3. So if I take some plane through the origin in R3, it will intersect this R2 in a line. So we're getting lines to RP2 ultimately from planes in R3. So that's how we can think of subspaces of a vector space as points, lines, planes, etc. Projective space. And that's where this idea of, that's another way to think about this flag business that we were talking about here. So if we have this D flag in Fn, so it was a bunch of nested subspaces. So we have the zero-dimensional subspace always, and then these bigger and bigger subspaces, with the last one being the whole K of them, the last one being the whole vector space. We can think of that as a bunch of figures in projective geometry, where these subspaces with their various dimensions correspond to figures of dimension 1 less in the projective geometry. So, in particular, for example, when we took the case that we looked at here, so this is the one that we were looking at, right? So we had, well, I don't want to give it away completely, so I'll ask it as a puzzle. So say we took this example with D. So we looked at what a D flag was like in terms of F cubed, but if we think of it as some kind of geometrical structure, geometrical figure on a projective space, what does it look like? What kind of thing is it? Just in this example. So I'll ask you, so in this example, what dimension of projective space are we talking about? Yeah, FE2, right? So we were talking about F cubed, so that means we're talking about FE2. So we're talking about the projective plane. If you like, you can think of F as R. So this has to do with projective planes. And what kind of structure on the projective plane, what kind of stuff is in the projective plane is this D flag amounting to? A point on a line on the plane. So this last box here gives you a fairly bland thing. There's just one choice of what this last thing can be, so that's not very exciting. So in this particular case, a D flag, in this particular case, it would just be a point on a line in the projective plane. So this is a point on a line. So that's a kind of geometrical structure that you could put on the projected plane. And so the kind of thing that I'm talking about when I'm talking about geometric representation theory is combining all the tricks that I've mentioned so far to get interesting group representations. So what am I saying? So I'm saying that GLN F acts on Fn. So it acts on the set of D flags on Fn. So this is my notation again, but now slightly modified. Set of D flags on Fn, where here D is any D-box Young diagram. So N-box Young diagram, uncombed. So I got from one group action to a more fancy group action by equipping this set with some structure and letting my group act on the set of those structures. But then we get a representation of my group, GLNF, on the vector space. The vector space coming from this set. So in vector space, say C, I can use complex if I want. C,
You mean rep of GLNF?
Representation of GLNF on C is a set of these D flags. Now, so this is like what I did in the case of N bang acting on C to the D of N. So it's formally very similar. In the last case, the N bang case, I said that we in some sense got all the irreducible representations of N bang sitting inside these guys. I believe that we don't get them all in this case. So to measure my ignorance, this question, which I'm sure some people know perfectly well the answer to, I'm a little fuzzier on, but I'm pretty sure we don't get all the representations. We don't get all the irreducible representations as sub-representations, but we get a bunch of them. I'm so confused about this that I think we might all get all the ones where, instead of working with complex representations, we use irrational numbers. Then I think maybe we get them all. Do you know that? So Jim may know that.
Right.
So you know how that we don't get all the irreps of GLN FQ
Oh, yeah.
this way.
Yeah.
And then there's these other representations that we have to talk about someday called cuspidals.
Yeah.
I was wondering, could it be possibly true that we get all the rational representations?
I never thought of that, so, I was thinking about it that way, I don't know.
Yeah, I don't know. I was sort of hoping that the other ones would require unity. Anyway, so I don't know. But we don't get all the last. Not all. Maybe here I should restrict to the case where finite field. Not all irreps of GLN, FQ, Y in these. So it doesn't work quite as beautifully as it did in the case of the symmetric groups, but we get sort of a portion of the representation theory of these GLNs that mimics the representation theory of the symmetric groups, in the sense that we're getting them from Young diagrams, and a whole bunch of the same formulas will work, but they'll all be Q-deformed. So you could say that Q-deforming the representation theory of the symmetric group gives us a fragment of the representation theory of GLN FQ. So that's something we need to talk about more. But part of my point here is that we really are talking about geometrical structures. So if D is this Young diagram, a D flag looks just like this. as long as you remember that this is a projective blackboard, on a projective plane. So it's a point on the line on the plane. Now, that's only mildly interesting as far as geometry goes. There's some interesting things that happen. So in particular, we'll be interested in relationships that can hold between these kinds of figures. So we'll often be thinking about situations where you have like a bunch of these flags. For example, it would be very interesting to think about this situation where you have 3 different flags stuck together like this. The reason why it's interesting to think about 3 flags stuck together like this is because if I've got 3 flags stuck together like this, and you've got 3 flags stuck together that way, so some other 3 flags here, then there's a unique symmetry of the projected plane that will map my 3 flags over to yours. So there won't be any Euclidean symmetry, of course, because the lengths get all squashed and stretched. But projective geometry is the geometry that, where all you know about is whether points are lying on lines, when lines are intersecting points, stuff like that. So it turns out that you find a symmetry that maps this in this way. Now, wait a minute. Is that true? I sure hope it's true for the projective plane. You're saying it's not unique?
Oh,
I thought this was the whole apartment.
yeah, but I don't think it's unique.
Uh-oh. Uh-oh. I'll have to think about what it is. So is there some perspective? This is a question about perspective.
Yeah.
So the way it's saying is there some other way to look at this picture, some other different perspective, where the picture looks different, but these 3 points in the picture look exactly in the same place?
So
I think I'll leave. I'm not going to be able to answer this puzzle because we've got about 0 minutes to answer it.
So we mean if
I'll
we
leave
have
that on the puzzle.
some relationship or order in the points, I don't want to say order, but where they stay in the same relationship with each other. Because, I mean, because clearly we can choose to map that bottom link to any one of those 3 points by a symmetry in some way, right?
Oh, I think Jim and I agree that there exists a projective transformation that maps these 3 points to these 3 points.
Yeah, I agree.
Right, but you're
We're
saying
just
that
asking
one
whether
is
it's
unique.
unique. So in other words, if I had some 4th point, do I know where that has to go? I'm not sure. I thought we better get that on. My last point, however, was going to be that there are certain kinds of symmetries of this situation that map those 3 points to themselves, not to themselves, but to each other, that permute those points.
But you can already move the 3 to any other 3 by affine transformation. Now you got more blockiness.
Uh-oh. Okay, so there's not uniqueness. That's too bad. It would make my story so much nicer. But it doesn't really matter. So, all I'm trying to say is that there are certain symmetries of this picture here, which are then going to symmetries of the projective space, which are just permutations of those 3 points. And so why am I caring about that? Well, that's because that's 3 bands. So I'm just saying that there's some nice relationship here between GL3 now, which is acting as symmetries of this projective plane, and 3 bands, which is acting as symmetries of just these 3 points here. And I guess I'll quit there. There's a lot more to say about that. Okay.